chemistry. This lesson is on more chemistry math. So accuracy and precision. The accuracy of a measurement indicates how close to a known true value it is. The precision of a measurement indicates how closely grouped the measurements are. So kind of the classic example is darts on a dartboard. So if you're throwing darts at a dartboard, you're trying to hit that center dot called the bullseye, and you can see that this person throwing the darts was all over the place. They weren't near the bullseye. In addition, their throws were not closely grouped together. Some are high, some are low, some are right, some are left. So the darts are not near the bullseye, the center dot, and they're not close together. So this is low accuracy and low precision. In the second example, this is low accuracy and high precision. The darts are not near the bullseye, but they are close together. So this would indicate, if you're measuring something in a lab, that maybe your scale isn't calibrated properly. You're trying to weigh something that's 5 grams, but it keeps coming out as 6 grams. So it's coming out with a consistent reading, but it's not close to the true value. So that would be good precision, but not good accuracy. Okay, next up we have high accuracy and low precision. So all of these darts are near the bullseye, but they're kind of high, low, right, left. So they're not real precise. They're not really tightly grouped together. So that would be high accuracy and low precision. So the darts are near the bullseye, but not closely grouped together. High accuracy, low precision. And finally, the darts are near the bullseye and are close together. So that would be high accuracy and high precision. So accuracy is measured by percent error. Percent error is the percent difference between the true value, assuming that there's a known value that's true that you could look up in a book or on the internet, and it's the difference between that and the measure value, the percent difference. So how do you calculate that? You take the true value that you looked up or that was given to you by a teacher, and you subtract the value you measured, that's your measured value, and you divide by the true value and multiply by 100%. So example, a student measures heat released from a reaction as Q, which is heat, we'll learn that later in the course, 15.7 kilojoules. The known value for the reaction is 16.5 kilojoules. So you plug those numbers in, there's the true value, 16.5, minus the measured value, is 15.7, divided by the true value, 16.5, and you multiply by 100%, and that gives you 4.8% error. The absolute value brackets, those vertical lines, mean the answer will always be a positive number. Precision is how closely grouped the measurements are to one another. So precision is determined by a measure called the standard deviation, and that's the Greek letter lowercase sigma, and that's the symbol for standard deviation, but it's also abbreviated SD, standard deviation. Standard deviation gives a number value for how spread out your measurements are. And there's the formula for standard deviation, so we'll plug the numbers into that in just a moment. So find the mean, that is an average. The mean is an average and standard deviation of the following sets of numbers. So set 1, the numbers are 19, 20, and 21. So to take the average, set 2, it's 10, 20, and 30. So to take the average of set 1, you add the numbers together, 19, 20 plus 21, divide by how many numbers you have, 3, and you get an average of 20. If you do the same thing for set 2, you get 10 plus 20 plus 30, you divide by 3, you also get an average of 20. So both of those sets of numbers have an average of 20. Both sets have the same average, however the values of set 2 are more spread out. You can see that just by looking at them. Okay, so let's take set 1 right here. The first thing you do, you make a 4-column table like this. You list the data values, 19, 20, and 21. In the next column, mean value, you list the mean that we calculated of 20. Then you subtract. That's called the deviation. You call it the difference. So 19 minus 20 is -1. 20 minus 20 is 0. 21 minus 20 is 1. And then you square the deviations. So -1 squared is 1. 0 squared is 0. 1 squared is 1. And then you add those deviation squares. So 1 plus 0 plus 1 equals 2. And that symbol is the Greek letter sigma, uppercase sigma, which means summation. You might have seen that in math class. It means you're adding the numbers. Over on the bottom left, you see n equals 3. That means the number of values equals 3. So we have the formula up there in the upper right, and you can see that we're going to put the number 2 up on the top where it says sum of deviations squared, that's the 2, and n, which is 3 minus 1, down on the bottom. So let's go to the next slide and do that. Actually, let's compute the value of set 2 first, okay? So the data values are 10, 20, and 30. The mean, again, was 20 for that set of data values, so you list that in the next column. Then you do your subtraction. 10 minus 20 is negative 10, 20 minus 20 is 0, 30 minus 20 is 10. And then you square those numbers. Negative 10 squared is 100, 0 squared is 0, 10 squared is 100. And then you add up the deviation squares. So 100 plus 0 plus 100 equals sigma 200, the summation. And n again equals 30. You have 3 values. So square the deviations and sum them, that's the 200. Okay, so there again is the same formula for standard deviation. Now we're going to go and do the calculation for each of these 2 data. Okay, so now we're going to take the standard deviations. So the standard deviation for set 1 is 2. That was the sigma, the summation of the deviation squared, over 3, the number of values, minus 1. You take the square root of that, you get 1. For set 2, the summation was 200. Then you have 3 values minus 1 also. Take the square root of that, you get 10. So you can see that the standard deviation is greater for set 2 than for set 1 because the values are more spread out. So the higher standard deviation of set 2 indicates that the data in this set are more spread out than the data in set 1. For a normal distribution, which we'll talk about on the next slide, 68% of the values will fall within 1 standard deviation of the mean. This small data set, just 3 values, is not enough data points to see that here. So this is a normal distribution, sometimes called a bell curve. So what does standard deviation really mean? A normal distribution, also known as a bell curve, has values evenly distributed around the mean, around the average. So the mean is right in the middle. It's the highest point in that curve. It's that symbol mu, Greek letter mu. So on a normal distribution, about 68% of the values will fall within 1 standard deviation of the mean. That's the Greek letter mu in either direction. So you can see there the pink area, 34.13% to the right of mu, 34.13% to the left of mu. That's a little more than 68% of the values are plus or minus 1 standard deviation of the mean. Now the blue area, if you added that in, that's 2 standard deviations, plus or minus 2 standard deviations. So if you added those percentages together, 13.59 plus 34.13 plus 34.13 plus 13.59, you'd get about 95% of the values fall within 2 standard deviations of the mean. And the light green area gets it up to about 99.7%. That would be a 3rd standard deviation from the mean. So 99.7% of the values will fall within 3 standard deviations of the mean. The pink area on the distribution to the right represents plus or minus 1 standard deviation from the mean. So let's take an example with a few more numbers. So the following shows the score on a 12-question quiz, and there's 22 values there. If you take the average of those, you'll get 7.6. You add them all up and divide by 22, you'll get 7.6. And you can see the red arrow is showing that right about where 7.6 is in between those numbers. If you compute the standard deviation of those values, you'll get 2.1. So that means that ideally about 68% of the values will fall between plus and minus 1 standard deviation of 7.6. So let's take a look at it here. This means that about 68% of the values should fall between 7.6 plus 2.1, which equals 9.7. That's where that red bracket ends on the right side. And 7.6 minus 2.1 equals 5.5. That's where the red bracket ends over on the left side, in between 5 and 6. We actually see 14 of the 22 values, if you count them, or 64% of the values fall within plus or minus 1 standard deviation of the mean. The discrepancy is due to the fact that the data does not form a perfect normal distribution. You can see it's kind of lopsided. It's also 22 is still not a very big set of numbers. If you got 100 or 1,000, then it would get very close to the 68%. Now we're going to take a look at a new subject, logarithms. A logarithm is an exponent. An exponential function is a function with x, the independent variable, in the exponent. Logarithms are the inverse functions of exponential functions. We'll talk about what inverse functions are here in just a minute. So 10 to the x equals y is an exponential function. If you've ever in math class done the function y equals x squared, that is not an exponential function, because even though it has an exponent of 2, that's not a variable. The variable has got to be in the exponent for it to be an exponential function. So y equals 10 raised to the x power is exponential. The inverse of that is the log, which log, that little 10 means log of base 10 of y equals x. So what does that mean exactly? It means that 10 raised to the second power equals 100. And then if you take the log base 10 of 100, it gets you 2. So what the log is telling you is what exponent do you have to raise that base to, that 10, in order to get 100? And the answer is 2. You have to raise 10 to the second power in order to get 100. That's what a logarithm tells you. So the parts of the log are the base. This is called the argument. You'll never hear us use that word, but that's what it's called. And this is the exponent. Log a means that log base 10 of a. But if there is no base, then the base is assumed to be 10. So if it just said log a, you would assume that it's base 10, because that's the base we work in every day with math. Natural logs are a special base. A special base that appears in nature is 2.718. The letter E represents this number. It's called Euler's number. So E equals 2.718. So E is not a variable. It's not a number that can change. It is always that number, 2.718. And it's kind of one of those magic numbers in nature and in mathematics, like pi, that seems to appear everywhere. And so this has a lot of applications in all types of sciences, is this E, this number E. A special symbol for logs with the base E is called ln. It basically kind of stands for natural log. A special base that appears in nature, so we'll repeat this, is 2.718. The letter E represents 2.718. That's called Euler's number. And a special symbol for logs with a base E is ln, natural log. So log base E of x equals ln x. So you never would write that log, L-O-G, base E. You just write ln, natural log, of x. Inverse functions are functions that reverse each other. For example, addition and subtraction are inverse functions. Square and square root functions are also inverse functions. Exponential and log functions are inverse functions of each other, and we're going to need to know how to use those in applications in chemistry. So let's start with the number 2. Now you're going to raise 10 to the second power, and that gives you 100. Now you're going to take the log of base 10 of 100, it gets you back to 2. So you started with 2, you ended with 2, because the exponential 10 raised to the x power, 10 to the second power, and log base 10 of 100 gave you a 2 back. So they reverse each other, and that's what inverse functions do. So start with 2, raise the base to this power, then take the log of the result, and it returns to 2. Now here are a lot of properties of logs. This is something that you would cover in a math class. I'm just going to highlight a couple of them. I'll just run you through all of them there. You can take a look at them and see if they look familiar to you from math class. But it's the last few that we're really interested in here, and that will come up in some of our chemistry applications. So the first one is number 8. So the log of a number a, some number a raised to the x power, is equal to the x brought out in front. You can take that x out of the exponent and bring it out in front of the log a. So log of a raised to the x equals x times log of a. So that's going to be an important property that we're going to use. 9 and 10 have to do with the inverse concept that we just talked about. So the 10 raised to the log of a variable x, or any number x in that case, will give you back x. It'll give you back that number, because the 10, the exponential 10 raised to a power, and log are inverses of each other. They reverse each other. Similarly, e and natural log reverse each other. So if you say e raised to the natural log of some number, it can either be a variable or a number, it's going to give you back whatever x is there. Over on number 10, If you take the log of 10 raised to a variable x, it will return x. Again, they are log and the exponential 10 raised to the x are inverses of each other, so they reverse each other and give you back the x. And natural log of e raised to the x will also give you back an x. So you have this in your reference sheet section, and you can refer to it as you need it. So let's take some examples. Find the value of x in the following equation. 4 raised to the 2 plus x equals 3.2. So you're asked to find the value of x, but it's up in an exponent. So how do you deal with that? So take the log of both sides. So log of 4 raised to the 2 plus x equals log of 3.2. In math, you can do anything to one side as long as you do the same thing to the other side. Okay, it's like a scale, you have to keep it in balance. So you take the log of both sides. Using Rule 8, you take that 2 plus x in the exponent and you move it out in front of log of 4. So the 2 plus x comes out in front of log of 4, and then that equals log of 3.2. So you see that right there. Now you can compute log of 4 and log of 3.2 on your calculator. So log of 4 is 0.602 and log of 3.2 is 0.505. So you have 2 plus x times 0.602 equals 0.505. Now it's just a basic algebra problem. You divide both sides by 0.602 and you subtract 2 from both sides. So solving for x by dividing both sides by 0.602 and subtracting 2, you end up with x equals negative 1.16. Okay, let's look at another example. Again, you can always pause and review these examples if they don't quite make sense the first time. They might the second or the third or the fourth. They eventually will make sense if you watch them enough times. So let's find the value of x in the following equation. So you have natural log of 2x equals 3.2. So now you have an x inside of a natural log. So you need to get it out of there so you can solve for what number it is. So you raise e to the natural log of 2x on the left and e to the 3.2 on the right. Again, anything you do to one side is legal as long as you do it to the other. So you can see what we did there. We took that entire equation up above and we took e and we raised the left side to ln 2x and we raised the right side e raised to the 3.2. Now, e raised to an ln is an inverse, so it's simply going to give you 2x. And e raised to the 3.2 is something you can compute on your calculator, and if you're not sure how to do that, we'll show you how to do that in class. So what you end up with is 2x on the left and 24.5 on the right, and now it's just a simple divide both sides by 2, and you get x equals 12.25. So let's look at what logarithms do. Logarithms serve two main functions in science. They linearize, that is, make a straight line out of a curved exponential function so that analysis becomes possible. The second thing they do is they scale down the outputs of an exponential function to make graphing possible. So here's a graph of the basic exponential y equals 10 to the x. So if you take the values of x 0 through 5 and you plug them in, what you'll end up for y values is y equals 1, so 10 to the 0 power equals 1. Remember, any number raised to the 0 power is 1. But now, as you go down all the way to 5, you got 10 to the 5th, that's 100,000. That's impossible to graph that on a piece of graph paper. You go from 1 to 100,000. Okay, so it's much easier to graph if you graph the log of that exponential. So the log of 10 to the x, and we recognize that at this point as being an inverse. So if you put in the values of 0 to 5 for x, you'll come out with the values of 0 to 5 for y. Now you can see that would be much easier to graph. That would be actually possible to graph that x versus y on a graph. So that's why graphing a log actually does what point number 2 says, which is scale down the outputs of an exponential function to make graphing possible. Okay, now let's look at the graphs. If you look at the graph of 10 raised to the x, if we plot an exponential graph, the graph will increase so quickly that it will not fit on a piece of graph paper. It also produces a curved line, which means we can't figure out things like the slope and so forth without using calculus. If you extended this graph to x equals 10, so y equals 10 to the 10th power, the red line, if your computer screen is about the same size as mine, the red line would reach beyond the moon. It's hard to believe, but it would reach that far. Now let's look at the graph. Instead of y equals 10 to the x, let's look at y equals log of 10 to the x. So plotting x against the log produces numbers that can easily fit on a piece of graph paper. It also linearizes, creates a straight line of the data. So unlike the graph on the left, this graph can easily display up to x equals 10, and you can use basic math that you've already learned to figure out the slope of that line. So it's easy to do analysis on that line. Alright, and that takes care of our lesson on more chemistry math. We'll start applying math to chemistry coming up in the next couple of lessons.